like to talk about is some more areas than very specific problems, and some sort of words of warning. I want to talk about problems that arise in essentially analysis applied to soft matter problems, and probably a much larger variety of problems. And the things I want to talk about or emphasize are one would be the role of dimensionality, and second I'll call symmetry or not. And here the main theme will be, although we are trained on the physics side, we are trained from birth to exploit symmetries of problems. It very often, as the analysts know, leads you very badly astray. And I want to illustrate that with some toy problems. And this will lead to some kind of problems involving shape. And there will also be some problems that involve singularities or defects, where these kinds of objects, you might call them emergent, emerge from the solution of some analysis problem. So you could call it, so there'll be shape problems will come in here, and 4 will be sort of emergence of defects, topological defects, singularities, zeros, and so on. So dimensionality, physicists have exploited a lot the properties of curves embedded in some space. And for example, all of polymer physics is about 1D curves and 3D, usually 3D flat space or 2D flat space. And that's a very, very rich theory and lots of long wavelength behavior of polymers. Doesn't really depend on what polymers are made up, and you can apply statistical mechanics and get wonderful results and so on. But the topology is rather limited. For a polymer, you have an open line or you have a circle. As soon as you move to a two-dimensional object, say, think of a membrane living in some space, maybe three-dimensional bulk space, then the problems get a lot richer because of the richness of two-dimensional topology and geometry. And really simple problems can be very hard. So I want to, 2 dimensions, illustrate that with the following problem. So supposing you have some L-shaped region like this. It's a 2-dimensional corridor. And it's of width 1. L equals 1 here. And you're moving 2-dimensional furniture around. So you're moving a sofa around. And it has to be maneuvered around this corner. Okay. And you want to know the shape of the largest area sofa that you can maneuver around this corner. Okay. So it'll have some area divided by L squared, which is 1 here, some optimal area A, and you want to find that shape. Okay. So this area, A star, is some constant times, well, it's pretty obvious you can make a semicircular disk which has, the radius equal to this length here, which has area pi over 2. So let's divide out by pi, divide out by pi over 2. So this is some constant times pi over 2. So anybody know what that constant is? So this is actually an unsolved problem. So it's not known. You can do a lot better than semicircular disk by cutting out keyhole-like shapes that enable you to rotate the thing around here. You basically have translation, rigid translations and rotations. So these kinds of problems, just moving up to 2 dimensions, not even any interesting topology here, just a right-handed kink. It's not even clear, exactly how to formulate it. It's some kind of variational problem, but it's not clear exactly how you would start doing this, as evidenced by the fact we don't know the solution. So shape kind of problems are very rich, and we have these kinds of problems in all over the place in soft matter physics. So my talk here earlier in this program, which you can look up on the web, was what is the shape of a 2-dimensional, say, symmetric liquid crystalline vesicle. And I showed that where it's easy to bend, in the limit of very low bending rigidity, it assumes a tetrahedral shape, okay? Rather singular kind of shape, interesting shape. And those kinds of problems, they're hard because of the 2-dimensional objects that you're dealing with. And on the soft matter side, you have the additional problem that there's some functional that you're minimizing on top of that, the energy of your object, say, energy minimizing problem. And those problems, not only very hard from the analytic point of view, they're also very hard from the computational point of view. We don't have very good algorithms when you have to minimize over some order on some manifold to be determined in the optimization process. There's another, so I probably won't have time to come back to many details of that, but there's a whole, so surf, some membrane, sigma living in some space, and could be 3-dimensional flat space or something else, has a whole variety of interesting optimization problems. Typically you have some energy that you're optimizing, and you have to determine the shape as well. Now I want to talk a little bit about this emergence of defects, and another illustration of where symmetry goes very badly wrong, even as far as the topology of the solution is concerned. And the toy problem for this case, this I learned from German mathematician Bernd Kewal, who has a lot of beautiful papers on symmetry breaking. This is really symmetry breaking in analysis. So this problem is the following kind. It's called the opaque square problem. So you have a 1 by 1 by 1 plot of land or shape like this, and you have to build a mirror, say. And the mirror has to prevent light getting from one side to any other side of the square. Okay? Or you can think of it as a flat piece of land under which there's a straight electrical cable, telephone line, and you have to dig a trench that's guaranteed to uncover that telephone line, 2D flat object. And you want the trench of minimal length, or the mirror of minimal length. Cost you to build this thing, so you're saying the cost is proportional to the length, so you're minimizing it. Everything's flat, so you're finding a curve, one-dimensional Hausdorff curve of minimal length that does this. So of course you could go around all 4 sides, which would be of length 4, but the light's going from one side to another side, so you only have to cover 3 sides, so that's of length 3. And then anybody who's thought about soap bubbles or minimal surfaces or anything like that will put in interior points. It's called a Steiner graph, and these interior points are Torricelli points, have long famous history and so on. So you get something like this, highly symmetric object, and this, so you can see anything going from here to here is blocked by one of these lines. They have to come out of all 4 corners because you could have light going across any of those corners. And this has length, this curve, gamma has length 1 plus square root of 3. It's nice. this is not the best solution. So you can do better. In this case, you can pretty much show this is an optimal solution. And the optimal solution is very surprising. So it has a freely terminating point. It has two connected components. So you have a point like this, and then you have something a little bit more like this in this corner, this quadrant, and you have this ending here in the middle, and this quadrant. Once you figure out this shape with two disconnected components, you can easily work out this angle from calculus. It's pi over 12, and the length is a nice number, root 2 plus square root of 3 halves. So here, you started with 8 symmetries, reflection symmetries of the square, and you break all but one of them. What's left is only reflection about this diagonal. All the other symmetries are gone. So 7 out of 8 of them are broken. So if you assume that the answer has anything to do with the symmetry of the square that you started with, then you go badly wrong. Doesn't give you any clue as to what the form of the answer should look like. So we can't really assume it in these kinds of problems. So there's an emergent topology here, two disconnected components. Okay? There's a lot of symmetry breaking, and so on. So the kinds of problems, go back over here, where of this kind of flavor that are, what did I do with the eraser? Oh, it's there. The kind of problems, at least that I know something about, where this kind of thing happens are in, so if you have order on a curved surface. So in this case, for example, you could look at a crystal on two-dimensional sphere, so the surface of a ball. Okay. This, so you can write a Hamiltonian for this problem, and it involves possible defects, because crystalline order on the sphere has to have some defects because you cannot have a regular triangulation of the sphere. Some minimal defects required by topology. But it turns out that actual ground states, so let's take n electrons on the surface of a sphere. Once n gets big enough, the actual number is not universal, depends on the microscopic potential, but it's fairly small, of order a few hundred. Once n gets big enough for almost all kinds of microscopic potentials, the ground state has extra defects, not just those required by topology. And you can make this very graphic in the case of the torus. Okay. Take a regular torus embedded in R3, so a bicycle tire, surface of a bicycle tire, that emits regular triangulations. But the energy of a toroidal crystal, just on the surface, two-dimensional, has defects. It has 5-fold coordinated points on the outside where the curvature is positive, Gaussian curvature, and 7-fold coordinated things on the inside, some finite number. That lowers the energy of the system. So in that case, the defects emerge as a solution of an energy minimizing problem, just like this kind of funny point here emerged as in this kind of a minimization, optimization problem. There are quite a few examples of this kind of emergent behavior of defects as energy minimizers, also in analysis and nonlinear sigma models, for example. Mappings, just a gradient energy of a field can be a liquid crystalline field or a scalar field. Mapping, say, from some domain onto taking values in S2 and maps into three-dimensional space. So sigma model things, or models of liquid crystals, they can have defects as energy minimizers, not set by topology or boundary conditions. So this gives you when sort of the situations in which this occurs, it gives you a whole very large set of open problems. And these kinds of structures, the defects themselves, they're points, say, where the order parameter vanishes, or you have diverging derivatives, gradients, okay, or zeros of fields. These are very, very special points. They're distinguished mathematically, they're distinguished physically, and it turns out that in many settings they can be detected also chemically, and probably are utilized in biological systems as well. So for example, one thing that people try to do is to create structures that replace atoms, structures on the nano to mesoscale. You know, you could take some kind of object with a defect and think of that as your atom. Okay? And then you can use defects, since they're marked points, special points, to attach ligands to make the analog of quantum mechanical bonds. Okay? So you can have the number of defects will determine how many bonds you can make, which is valence. You link up bonds with the ligands, and the arrangement of the defects on a given, I call them superatoms, the arrangement of defects on a given superatom will determine what kind of directional bonding you can make when you link these things up. So that will determine the possible molecules you can make by the valence and the kinds of directional bonding you can get. Once you have molecules, you can try to make bulk materials with these things, with a library of superatoms that's not constrained by quantum mechanics, but it's determined by other principles, the number of defective regions and the global geometry of relative arrangement of the defects on that surface. So that's an infinite number of open problems right there. People also try to link things up in very different ways, not using specificity of defects, but coating them with things like DNA, and then you use complementary bonding of DNA to tie things together and so on. That's a very different but also interesting approach with a lot of open problems. And then after that, there are very deep problems that I'm sure that other people will talk about here, because there are many more experts, but there are problems like granular media, where we don't even have a good formalism. Okay? It's a system that's given by zero temperature. It's not apparently easily described by statistical mechanics. So we don't have the formalism to even start the problem. So that's very challenging. And then there are a whole host of problems that involve complex spatial and temporal behavior. I think one very good example is neuroscience. I know almost nothing about it, but every time I look at it, you have interesting physical structures and interesting communication going on, but it's very spatially inhomogeneous, and it's very dynamic. So you have what you would call universality classes of structures, but they're more than one, and they're linked together intermittently, dynamically, on and off, and so on. Again, we don't even have the formalism to begin to describe them. So that's interesting open problem where you may get completely stuck, but you may do something revolutionary. Okay, I think I'll finish there.
Thank you. Well, it would be nice if we asked questions to him.
Can I ask a question on an open problem?
Yes.
In this opaque square problem, why are you, if it's just the distance between 2 points, then I understand why you are just joining them by straight lines. But if it's a disconnected set of points, then, is it clear?
No, you mean for the solution?
Yeah. Why is it not, or is it proved that, any sort of a curve, which is not a straight line, will never be a minimum, or will not be a minimum?
Yes, you won't get non-straight lines because there's no, it's purely Euclidean problem. There's no,
But even if you
the
have
blocking light, or you're not going to, if you curve the line at all, you're going to increase the length. You can replace that by an equivalent straight line that does the same job. All it is doing is blocking light that gets from here to here. That's the only requirement. So any curvature in the line can be equally well done, or can be replaced by a straight line with smaller length. And that will still perform the blocking, the mirror, or uncover the telephone line as a trench. You could ask whether you can have more disconnected components.
that's right. That's right.
This was my
That's
question.
why-
Is
why-
it uniqueness proved in this case?
I would say, yes, it's proved for this case, but you do get a high number of connected components if you change the shape, the square, to something else. And you can take an n-gon, and you can even take n going to infinity, which is the circle, and the solution in that case is not 2 pi. The solution is pi plus 2. And it has an infinite number of disconnected components. But in this case, you can prove it's 2. K-wall.
So if I take a beam of light
Yeah.
from a point that is epsilon to the left of the projection of the central point onto the bottom,
Here?
take there and
Just over here?
yeah, but I want it close to the, so move it over towards the middle. So you want to go from there and shoot it, just missing the point upward,
Okay.
and it keeps on going. It hits there.
Yeah.
Now, doesn't it hit? What happens after that? It looks to me like it hits the other.
Solved. Just has to block it. We're not tracing the light. Just has to block.
Oh, just absorbs it.
It's not
I
reflected.
thought
Cannot reach this side.
Yeah.
Cannot reach this side.
You said mirror, so I thought you meant.
It's a mirror.
Yeah.
It just has to block the light. Or it's a trench that guarantees that you uncover the telephone line underneath. You just have to hit it and you're done.
I see. So it's okay. But if it were a mirror, it would hit the other side. If it were
You mean by reflection?
yeah.
I think
Well,
you mean dark sheet.
That's not
on
the
mirror.
problem, but if you start tracing the reflection, even can it get, can get to,
It can get to the other side there.
yeah, no, that's not the problem.
As a
Of course.
reflection problem,
Reflection go to here, no, it just has to block it.
so it is
Once.
completely absorbing.
Yes,
And the reflection problem, as it is solved.
I don't think so. It sounds like one of those chaotic billiards problems.
But the first
John.
problem, I remember once reading a paper of Gil Strang on moving some object through some. Oh, do you know this?
No, I don't know that one.
You may have won a convex surface, and if you've ever moved surface, you know that the fact that they're not convex can get you around corners.
Yes. So the best solution for the sulfur problem is due to Gerver. And, there's a solution due to Hammersley, which is much, much better than pi over 2. And it's a handset problem, so it looks something like you start with a rectangle like this, you add semicircle here, and then you cut out. For this kind of problem. This enables you to maneuver around the corner. And then Gerver has a solution quite a bit better than that again, and it has like 17 little pieces of this. This has 3 pieces basically. 1, 2, 3. He has 17 with little, so you can start trying to improve this. But what is the method that will sort of really lead you to the optimal solution? Not known. You can it's just tinkering, doing a little bit better, cut this here, cut this there, and so on.
It might not be an optimal.
Might not be one.
Yeah.
There's an upper bound known, and there's the lower bound known, pi over 2, and we're improving the lower bound. So this is sounds so, this is a sort of analysis version of those number theory problems that sound very, very simple and are very, very hard. It's all virtual two-dimensional physics.
Suppose you have a constraint on the perimeter.
It makes it even harder, usually.
But it could prevent shapes with many bits and bytes
Yes.
attached. Right. So it might make the problem easier.
It could. Yeah. It could. Basically, all bets are off because once symmetry is not a big thing to exploit, constraints change the symmetry, but so what? They can improve things by eliminating roots and possibilities. Yeah.
The perimeter is not very interactive. It's either both infinite or infinitely small. So if you take it upper limit, then
Just prescribe the perimeter.
the given perimeter.
Prescribe the perimeter. That was the constraint on the perimeter.
Yes, this was a constraint only on the area, finding the maximum area. We fix the parameter, that gives you removes
Change
a
the
lot.
problem, you make it easier.
Right.
Maybe.
Removes a lot of possibilities. It lowers the dimension.
Just for fun.
Basic solutions.
Well, let us thank our speakers today, and we reconvene.